Hello everyone, this is Group C8. Our project is AI Meets Beauty. My name is Minghui and my teammate is Kai Wen. AI Meets Beauty is an online challenge holding at this time. We can take a brief look at the challenge. The dataset of the challenge is Perfect 500K. Perfect 500K is a collection of 500,000 images of beauty and personal care products derived from dominant e-commerce websites as shown here, including Amazon, Yahoo, Target, JD, Walmart, etc. It is really vast in scale and rich and diverse in content. This lipstick on the left is a sample of image in the dataset. The main task of this challenge is, given a real-world image containing one beauty or personal care item, such as the lipstick on the right, the task is to match the real-world example of this item to the same item in the Perfect 500K dataset. This is a practical but extremely challenging task, given the limitation that only images from e-commerce sites are available in the dataset, and no real-world examples will be provided in advance. In the project, Kaiwen and I will try solely data-driven methods, especially deep learning, to solve the problem. There are two major challenges. The first is, for a product, there is only one image in the dataset. This is called one-shot learning. What that means is that for this recognition application, we need to be able to recognize one product given just one single image. The performance of deep learning is all about data, but historically, deep learning algorithms don't work well if we have only one training example. One seemingly useful approach is to input an image, feed it into a convolutional network, and have it output a label using a softmax unit, with several outputs corresponding to each of the products. This generally does not work well without additional processing, as the training set for each label is so small that it is not enough to train a robust neural network for this task. Also, this approach cannot scale. For the original data challenge with nearly 500,000 different labels, we just cannot create output layer with that many units. Another challenge is that the dataset doesn't have a clear label as an output of neural network. The label in the dataset is a short description of products in different languages, which is not that useful as binary or one-hot encoding label. In this project, Kaiwen and I propose different methods. My method is Siamese network with triplet loss. Before further introducing it, I need to tell you my preprocessing tricks. As we only have one image for training, as I mentioned, we need data augmentation to generate more pictures of the same label for training. First, we found 5 background images on the web. Each is 128 by 128 pixels. By briefly observing a small set of the training set, we discovered that most of the images have a purely white background for better promotion. Taking advantage of this feature, we filter out parts of the image by the grayscale value of each pixel, reshape it, and pad it with the backgrounds we chose in the previous slide. In this way, we obtain fixed-size images of the same product with different backgrounds. We use 4 backgrounds for training and a 5th background for test. So to carry out one-shot learning, what we do instead is learning a similarity function. In particular, we want a neural network to learn a function which is going to denote each input image as a vector. Then, for pairs of image, we calculate the Euclidean distances between them. So, if the images are considered of the same product, we aim to output a small distance, while if the images are 2 very different images, we aim to output a relatively large distance. This is the details of the architecture of Siamese network. Generally, it is composed of several convolutional layers, followed by some pooling layers, and some batch normalization layers. At the end of the network, the output is flattened into a long vector, and it goes through a densely connected layer of a fixed number of units, followed by an L2 normalization layer. After all, we get a vector of 0 mean and 1 variation. One way to learn the parameter of Siamese network so that it gives you a good encoding for the images is to define an applied gradient descent on the triplet loss function. To apply the triplet loss, we need to compare pairs of images. Given a pair of images of the same product, we want their encodings to be similar, whereas given a pair of images of different products, we want their encodings to be quite different. In the terminology of the triplet loss, we always look at 3 images at the same time: one anchor image, one positive image, and one negative image. Denote anchor, positive, and negative images as A, P, and N, respectively. We want the distance between anchor and positive to be smaller than that of anchor and negative. So intuitively, we can get a loss function like this. So in this way, if the the distance between anchor and positive is smaller than the anchor and negative, we can get a 0 loss, so that the neural network doesn't need to change. But otherwise, the loss would be positive, and we need to change the loss function. But this is not working in reality. When training the network, if the network outputs 0 vector encodings, which is highly probable at the beginning, the loss is always 0, and the neural network stops learning and gets stuck there. So to prevent the neural network from doing that, what we are going to do is modifying this objective to this way, so that we can enforce the difference of 2 expressions to be a bit smaller than 0. It can be achieved by adding this alpha to the subtraction, and then the loss function now provides a margin between the difference and 0. If the anchor, positive, and negative images are chosen randomly from your training set, one of the problems is that sometimes the constraint is very easy to satisfy. To construct an effective and efficient training set, we choose triplets that are hard to train on. We call them hard triplets. In particular, after we select an image as an anchor, like this, we only select an image of a different product but with the same background, negative. But we select the same product with a different background to be positive, so that we can always drag positive closer to anchor and pushes negative images away. In the beginning of the experiments, we tried AlexNet-like network, but the AlexNet-like network does not output a dense vector. For the purpose of rich activation, we instead use a convolutional neural network with inception. Inception is composed of inception blocks, like it is shown in this image. When we get an input from previous layers, we don't let it go through a single layer. Instead, the input goes through several paths. Each path contains some convolutional layers or pooling layers with padding and batch normalization. And finally, we concatenate the outputs of the paths together. In this way, the neural network can learn which path to choose by itself, and the activation result is much richer, like it is shown here. The method of Siamese network with triplet loss does not work very well. After 100 epochs of training, the network still does not converge. According to my analysis, there are 5 potential reasons causing this problem. I think the first 2 ones are the most probable. The first one is my way of data augmentation is too much, so that it's hard for the neural network to learn a pattern among the images. The second is the batch size is too small, so the training set gets stuck in a saddle point. We can increase the batch size and sum the loss accordingly. Later, Kai-Wen will introduce his method, and his method will give us better performance.
Hello, this is Kai-Wen. So first, I want to talk about 2 major challenges we kind of face when we try to solve this AI meets beauty challenge. So basically, the first thing we observe is there's only one image per label. So the second challenge we observe is the label are in many different languages, so it's not very useful to us. So next, I'm going to discuss how we kind of address these challenges. The first thing I want to address is how do we increase the training data set. So basically, we can crawl images based on, let's say, similarity. But there's some problem if we simply crawl images based on similarity. So for example, if the given image is the front of the product, then if we crawl based on similarity, all the returned images will be in the front of the product. The back will be missing because they are visually not similar to each other. So in this way, we run the risk of overfitting if we only crawl images based on similarity. Thus, we also need to crawl images based on keyword or label. However, like I previously discussed, the label is not very useful because it's in many different foreign language. So next, I'm going to answer like how do we get a real label. So before I do that, I also want to say like sometimes the first 2 approach they will both fail. So in this case, like by observation, most of the images in a perfect 500K dataset are cloned from e-commerce website. Thus, it's possible for us to do web scraping using Selenium and Google Chrome Drive. The last thing I want to mention is data cleaning is kind of challenging in this problem because we kind of construct our own data set. So the images we crawl from online website, it can have some really weird namings. It can be corrupted files. Sometimes the URLs provided in the original data set, it can be broken. And also sometimes the images we get from the Google Images search API, it can be in incorrect formats. So this thing will cause carriers to crash during the training process. So next I'm going to answer how do we label the data. So basically we surveyed a number of APIs, includes like AWS Recognition, Microsoft Cognitive Service, and also Google Cloud Vision API. So after performing some experiments, we found out that Google Vision API works the best. So basically the label with the highest confidence is returned to serve as the keyword to label the data. There's also many things that needs to be addressed when we are training our model. So basically, the first thing is in the real life, the product can be of arbitrary size and orientation. So basically, the size of the product can be scaled in real life. So its orientation can also be changed. Thus, when doing the training, we should not make any prior assumption about the size or orientation of an object. The second thing is variation in the environment. So basically, in the real life, products can be placed in different environments. Environment changes such as brightness, indoor, outdoor, and background noise should be taken into consideration. The third thing is large variation of features. Uh, so although all objects in this data set, they kind of belongs to the same category, which is a beauty product, but there are also many different subcategories. And actually, in the product in these subcategories, they can vary a lot. So um, this kind of explains like why there would be a large variation of features. So the last thing is the noise in the dataset. So because most of the images in the dataset they are crawled from online websites, thus certain methods that require a very high image quality may not work well in our scenario. So next I'm going to cover some background knowledge about data augmentation. So one key technique used in data augmentation is called affine transformation. So affine transformation is a linear mapping method that preserves points, straight line, and planes. Sets of parallel lines remain parallel after an affine transformation. An affine transformation technique is typically used to correct for geometry distortion or deformation that occur with different camera angles. So, for example, satellite imagery uses affine transformation to correct for wide-angle lens distortion, panorama stitching, and image registration. Transforming and fusing the images to a large flat coordinate system is desirable to eliminate distortion. This enables easier interaction and calculations that don't require accounting for image distortion and deformation. So here's a table that kind of lists some very popular affine transformation options. So for example, translation, scale, shear, rotation. So it's worth noting these operations, they can be combined together. So here are some sample effects. So image classification, even with convolutional neural network, is kind of challenging because in order to train an accurate model without overfitting, it will require millions of images. So I think it will be impossible for us to crawl this much image during such a short period of time. So I surveyed several methods. The first one I find is handcrafted feature extraction using color signature and gray level co-occurrence matrix. It basically first decode an image into RGB value matrix. From the matrix, you can obtain a color histogram, and the color signature can be calculated through gray level co-occurrence matrix. So this method sounds pretty promising at first, but one problem with this approach is it requires high quality image. But most of our images, like I mentioned before, are obtained through online websites, so the quality is not very good, and thus the color signature is not very accurate. The second method I surveyed is transfer learning. So it turns out that it fits our need, and indeed is the method that helps us achieve the best accuracy. Also, we kind of build a simple convolutional neural network that serves as a baseline. So basically, it's the simple convolutional neural network contains three convolutional layers followed by max pooling and a dense layer. So the accuracy achieved by this simple convolutional neural network is around 78% accuracy. So next, I'm going to talk about what is transfer learning and what's its difference compared to classic machine learning. So basically, in classic supervised learning scenario of machine learning, if we intend to train a model for some task in domain A, we assume that we are provided with label data for the same task and domain. So if we look at this figure, we can see that the task domain of the training and test data of our model A is the same. The traditional supervised learning method breaks down when we do not have sufficient label data for the task or domain that we care about to train a reliable model. So basically, you can think of it as in traditional machine learning, the model you train kind of inherited the bias of the training data set, and it does not know how to generalize to a new domain. So transfer learning allows us to deal with these scenarios by leveraging some already existing label data of related task or domain. So we try to store this knowledge gain in solving the source task in the source domain and apply it to our problem of interest. In order to implement transfer learning, we first need to obtain some pre-trained models. So after we obtain the pre-trained models, we can use it as some kind of feature extractor for our problem of interest. So basically, we remove the fully connected dense layers from the pre-trained model and add a new one to train based on the extracted feature. So this is how we can leverage a model trained on a source task to our task of interest. So on the two pre-trained models, we can observe is VGG16 and ResNet50. So both of these models, they are trained on the ImageNet dataset, which is a really popular dataset that contains millions of images. So VGG16 is a pre-trained model that gave state-of-the-art result on ImageNet dataset. It has 16 layers and about 16 million training parameters. This network is characterized by its simplicity. It uses only 3 by 3 convolutional layers stacked on top of each other in increasing depths. Reducing volume size is handled by max pooling. It also has 2 fully connected layers, each with 4096 nodes, then followed by a softmax classifier. ResNet is a pre-trained model provided by Microsoft. So as its name suggests, it has 50 layers. So maybe we can take a look at the architecture of the VGG and ResNet. So on the left-hand side, I have a VGG architecture. On the right-hand side, I have a ResNet architecture. So one thing you can observe is in the ResNet architecture, it contains much more layers. So we compare the performance of the two pre-trained models and find out that VGG16 provides better performance for our use case. So I think the reason is most likely because ResNet50 has too many layers. So the back propagation failed to update the weights of the initial layers properly. So because if you remember, like we remove the fully connected layers and hope to update the weights of this layer in order to solve our problem of interest. So in the ResNet case, there are too many layers, so the back propagation is not very efficient. But in VGG16, there's less layers, so the back propagation is kind of more efficient. And indeed, VGG16 is more widely used as a feature extractor in transfer learning. So here's the accuracy and the loose plot graph. So the best result we were able to achieve is around 91% accuracy. So now I'm going to give a demo session about the web application we built. So this is the initial user interface, and you can click on the upload image button. So for example, I'm going to try this one first. Now you can see we get our predicted result. So this one is the image URL. We can click on it. Yeah, so you can see like the prediction result is pretty accurate. So the dominant color is implemented by K-means clustering algorithm. It kind of explains why these images belongs to the same class. The similar products is based on image similarity. So you can see like compared to the original image provided in the original data set, this image is kind of from a different angle. So next I'm going to try some images with background noise. Yeah, so we're going to try this one. Yeah, so we get a result. And we can click on the link. Yeah, so you can kind of you can see they are the same product. So you can see like in this test image, an object is kind of rescaled and also rotated. It was also putting a pretty noisy background, but our model was still able to predict the correct label. So for example, this one, it has background noise. It also has like two products showing on the same image, but they are like the same product. So if we click on the link, yeah, you can see it's basically the same product. We can try one more. Yeah, so we get the result back, and yeah, if we take a look at it, obviously it's the same product. And in this case, there's also some background noise because the product was kind of placed in a real life scenario. Yeah, you can see our model works pretty well. So I hope you find this application interesting and useful. Thank you.